Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Welcome to our discussion on Bayesian causal discovery. Today, we'll explore its challenges and how optimization techniques, time series analysis, and frameworks like DoWhy and Pgmpy can enhance its performance. We'll also delve into real-world applications, highlighting the power of Bayesian methods in drawing causal inferences from observational data. What are some key challenges faced in Bayesian causal discovery, particularly regarding data quality and result interpretation? And how do these challenges influence the choice of methods used in practice?
In Bayesian causal discovery, there are several key challenges, especially concerning data quality and how to interpret the result. First, think of data quality like the ingredients you use to bake a cake. If you have rotten eggs or stale flour, the cake will not turn out well. Similarly, in Bayesian methods, if the data is incomplete or has errors, the conclusions drawn can be misleading. This can be particularly problematic when trying to make strong claims based on the model's outcomes. Second, interpreting the results from Bayesian statistics can be tricky, like trying to read a map without clear direction, because Bayesian methods rely on certain assumptions about the data. If those assumptions are not accurate, the interpretations can lead to confusion. It's important to perform independent tests, much like a chef tasting the cake before serving, to ensure that the results are valid and trustworthy. These challenges significantly influence the choice of methods used in practice. For example, if the data quality is questionable, practitioners may prefer simpler models that are less sensitive to errors. Additionally, when the stakes are high, such as in medical research, more rigorous validation processes are adopted to confirm the findings. In summary, just like how the best chefs choose their recipes based on the quality of their ingredients and their understanding of cooking technique, data scientists must carefully select their Bayesian methods based on the quality of their data and the clarity of their interpretation.
What optimization techniques, such as Bayesian optimization and BangLearn, have been shown to enhance the performance of Bayesian causal discovery methods? And can you provide specific examples of how these techniques address common challenges in this field?
Bayesian optimization techniques play a crucial role in enhancing the performance of Bayesian causal discovery methods. One prominent example is the Bayesian optimization library, which helps find the best possible value of a function with minimal attempts. Imagine trying to find the highest point on a hilly landscape, instead of checking every spot. This technique allows you to make smart guesses about where the high points might be, speeding up the search. Another example of optimization is using Bayesian methods for grid searches and tree-based algorithms like XGBoost. Traditional methods can be like searching for a treasure by digging up every inch of land, which is time-consuming and wasteful. By applying Bayesian optimization, it's like having a smart map that points you toward the most promising areas, thus saving time and resources. These optimization techniques address common challenges in Bayesian causal discovery, such as the computational burden of processing large datasets. By making the search for optimal values more efficient, they help data scientists to quickly refine their models and draw better conclusions from their data. In summary, just as a skilled treasure hunter uses intelligent tools to locate treasure more efficiently, Bayesian optimization techniques enable researchers to navigate complex data landscapes more effectively and enhance their causal discovery efforts.
How does the integration of time series analysis with Bayesian methods improve the understanding of dynamic relationships over time? And what unique advantages does this combination offer in the context of causal discovery?
Integrating time series analysis with Bayesian methods enhances our understanding of dynamic relationships over time, by allowing us to model how changes happen and assess their impact. Think of this combination like watching a movie unfold, instead of seeing just a snapshot. You can observe how events develop, which helps to clarify cause and effect. For instance, when a business runs a marketing campaign, it might observe a spike in sales. However, that spike could be due to various factors like seasonal trends or random chance. Bayesian time series analysis helps to separate genuine effects from mere coincidences by modeling expected behaviors over time. It allows businesses to estimate whether the increase in sales was really caused by the marketing effort, or if it would have happened regardless. One unique advantage of this combination is that it can quantify the impact of interventions, much like a scientist testing a new medicine on patients over time to see how effective it is. The Causal Impact Library, for example, uses a Bayesian structural time series approach to analyze the difference between expected and observed data after an intervention. This means businesses can make informed decisions based on how effective their actions are in real-world situations. In summary, merging time series analysis with Bayesian methods provides a clearer view of how actions influence outcomes over time, offering businesses valuable insights into the effectiveness of their strategy.
What role do frameworks and libraries such as DoWhy and Pgmpy play in enhancing the usability of Bayesian causal discovery techniques? And how do they support practitioners in overcoming common challenges associated with these methods?
Frameworks and libraries, like DoWhy and Pgmpy, play a vital role in making Bayesian causal discovery techniques more accessible and user-friendly for practitioners. DoWhy, for instance, is designed for supervised causal approaches and helps users focus on specific treatment and intervention variables. It can be likened to a guidebook that gives clear instructions on how to set up an experiment and analyze the outcomes, making it easier for practitioners to draw causal conclusions from their data. On the other hand, Pgmpy focuses on unsupervised causal discovery, allowing practitioners to uncover relationships from observational datasets without predefined guidance. Think of it as a treasure map that helps researchers explore and find connections in the vast landscape of data, even when they don't have a clear idea of what they are looking for. Both of these libraries address common challenges associated with Bayesian methods. For example, they provide pre-built functions and pipelines that streamline the process of discovering causal relationships, effectively reducing the complexity and time needed to analyze data. This means that practitioners can spend less time wrestling with the technical details and more time interpreting their findings. In summary, frameworks like DoWhy and Pgmpy enhance the usability of Bayesian causal discovery techniques by providing structured guidance and simplifying complex processes, helping practitioners to effectively navigate the challenges inherent in causal analysis.
What are some real-world problems that Bayesian modeling can effectively address? And how do these applications illustrate the strengths of Bayesian methods in causal discovery?
Bayesian modeling can effectively tackle a variety of real-world problems, illustrating its strengths in causal discovery. Here are some examples. 1. Healthcare and disease pathogenesis. In the medical field, Bayesian methods can help model the progression of diseases over time. For instance, when researchers want to understand how a treatment affects patient outcomes, they can use Bayesian models to analyze observational data instead of relying solely on controlled experiments, which can be costly and time-consuming. 2. Marketing campaign analysis. Companies often face challenges in determining the effectiveness of their marketing strategies. Bayesian modeling allows them to analyze sales data before and after a campaign, helping to estimate the causal impact of the marketing efforts. This can be particularly useful when running multiple campaigns simultaneously, or when external factors, like seasonality, could confound the result. 3. Social sciences and behavioral research. In social sciences, researchers might want to study the impact of social programs or policy. Bayesian models can help evaluate the causal relationships by analyzing data collected from observational studies. This is crucial when controlled experiments are not feasible due to ethical or logistical reasons. 4. Environmental studies. When studying the effects of environmental changes, such as climate change, Bayesian methods can be used to analyze complex interactions between various factors. Researchers can model how changes in one variable, like temperature, might causally affect another, like species migration, even when direct experimental data is not available. These applications highlight the strengths of Bayesian methods, such as their flexibility in handling both supervised and unsupervised data, their ability to incorporate prior knowledge and assumptions, and their robustness in dealing with complex relationships in data. By allowing researchers to draw causal inferences from observational data, Bayesian modeling provides valuable insights in situations where controlled experiments are impractical.
Thank you to our esteemed audience for your engagement. Throughout our discussion, we have explored the complexities and challenges of Bayesian causal discovery. Challenges with data quality and interpretation demand careful method selection. Optimization techniques like Bayesian optimization aid in finding optimal values. Integrating time series analysis enhances understanding of dynamic relationships. Frameworks simplify implementation and address challenges. Real-world applications in healthcare, marketing, social sciences, and environmental studies exemplify the strengths of Bayesian modeling in causal discovery, empowering researchers to draw causal inferences from observational data. We hope this discussion has deepened your understanding of this field. Embrace the challenges and advancements, and continue exploring the fascinating realm of Bayesian causal discovery.